Thank you. Yeah, my name is Sarah, and I'm very happy to present to you our joint work with Hedi Hadiji, Tim van Erven, who's sitting up there, and Mathias Staudigl. So this work is on an online learning approach for repeatedly played generalized Nash equilibrium problems. And to motivate our approach and our research question, let me start with a motivating example. So for this, consider the electricity market. So on the electricity market, at each time step t, we have agents who want to sell or buy electricity, of course at a good price for themselves. And then for the electricity market, we have this additional requirement that the utility frequency needs to be kept at 50 Hertz, that's for the European power grid, with a very low tolerance region, so that's 0.2 Hertz. So all the agents, while interacting on this market, have to satisfy joint constraints. And in case they violate these joint constraints, this might lead to a blackout. And I guess you all agree with me that a nationwide blackout it comes at very high social and economical costs. So that's something which all the agents want to avoid at all costs. So the problem I described can be stated as a repeatedly played generalized Nash equilibrium problem. So more precisely, the protocol we are considering is the following. So we have n players in this game, and at each time step t, each player chooses an iterate xt of I, and after choosing this iterate, they will suffer loss with respect to the utility function. And if they violate the shared constraint, then they have to pay plus infinity. So this is modeling the sort of game over scenario in the case of a blackout. Now, just with this protocol, there's no chance at all that the players can guarantee feasibility. So therefore, what we allow in this work is a limited amount of communication between the agents. More specifically, before committing to the next iterate, the players choose a set ST of I, and they communicate these sets to all the other players and receive also the sets from the other players. So based on these side information, the players then choose their next iterate. And having the side information, we may hope for always satisfying the constraints. So you can think of these STs as a sort of region the players indicate to each other where they want to play, ideally. So the goal of generalized Nash equilibrium problem is ideally to converge towards a generalized Nash equilibrium. So let me define what this is, and first let me remind you of what the Nash equilibrium is. I'm sure you are all familiar with that, but just let's recall this. So in an n-player game, we call U a Nash equilibrium if none of the players has an incentive to unilateral deviate from this U. And notice that this deviation is with respect to the constraint set for this player. In this case, the constraint set is the probability simplex in dimension di. Now for the generalized Nash equilibrium, we again have this requirement that none of these players has an incentive to unilateral deviate from this Nash equilibrium. But now the deviation is not with respect to the probability simplex, but with respect to the shared constraints. So in this case, I denoted this with xi. And this xi depends on the actions of all the other players. So this makes the problem more difficult. And what we want to do is give an online learning algorithm for which, when all the players follow this online learning algorithm, they can always satisfy feasibility. So in this work, we introduce a method which we call online feasible point method. So it's defined for each individual player. And in essence, it's just variation of a gradient descent method. So gt of I denotes the gradient with respect to the utility function. And the updates of the sets st and the iterates xt happens with respect to these gradients. Then the algorithm proceeds in phases. So each phase is terminated if a termination criterion is triggered. And if this termination criterion is triggered, then the players shrink their set st of I. So they give themselves less freedom and indicate to the other players more precisely where they want to play for the next iteration. Now, of course, I'm glossing over a lot of details here. So actually, the most challenging thing for defining this algorithm is to define this termination criterion and these two step sizes and balancing all of these criterions. However, under the right definitions, we can show that if all players follow this online feasible point method, they will always satisfy feasibility, and they can guarantee convergence with the right choice of step sizes towards the Nash equilibrium. So UI is the Nash equilibrium here. However, we cannot show this for all classes of generalized Nash equilibrium problems. So we are considering a subclass of generalized Nash equilibrium problems, which we call strongly benign generalized Nash equilibrium problems. And for this specific class, we can give these strong guarantees. Now, for those of you who are familiar with online gradient descent or optimization, standard optimization methods, you might realize that this convergence guarantees we give here are a strange mixture between convergence rate you would expect from an online to batch conversion, so that's with the square root of t, and convergence rate you might expect coming from classical convex optimization problem with strongly convex optimization, strongly convex functions. So from this we get this exponential rate. So the reason for this is actually that behind the scene our proof relies on an inexact gradient descent analysis. So that's one side result which we consider might even be for interest on its own. Furthermore, we also derive sublinear regret bounds for the individual players, which gives some sort of robustness guarantees with respect to the incentive of deviating from this online feasible point method. And furthermore, we also relate this subclass of generalized Nash equilibrium problem, so the strongly benign generalized Nash equilibrium problem, to existing classes of generalized Nash equilibrium problems, such as problems satisfying Harcos condition. Then in recent years, there was some growing interest in the online learning community in online algorithms with time-varying constraints. With varying constraints, where the constraint sets might even be chosen adversarial. And we also provide some results for that. And we show that with the strong requirements we have here, we can satisfy feasibility at all time steps because the constraint sets are not chosen adversarially, but endogenous to the system. And we believe that this direction, where we here don't have adversarial constraints, but some easier setting, might be an interesting setting for this line of research. So we also have a collection of further interesting research questions emerging from this work. So if you are interested in that, please come to our poster, and we are happy to talk about more details regarding our algorithm and more details regarding these potential future research questions. So thanks, that's from my side.
So that's interesting. First of all, I wanted to quickly make a remark about the electricity case. In the electricity case, there's another constraint as well, right? So the case, because electricity is not something that you want to store, so if nobody buys, that's also bad, I imagine. But okay, let's forget about that.
It's a simplified
Sounds
example.
good, sounds good, sounds good. I wanted to ask you about the connection between this sort of problems and familiar problems such as approachability, where the goal is not just to do regret minimization with respect to a scalar, but to bringing an average vector closer to a region, which could capture the constraints. But then I'm not sure how you could encode the Nash constraint in that case.
So you are thinking of something like Blackwell's approachability?
Yes, 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 for example. And there's a family of course, yes.
That's a very interesting question. I don't know is the honest answer, but it's definitely an interesting question.
Sounds good.
To think about it.
Anyone else? Thank you. So you have like a, guarantee, you have to be feasible every step or else you pay infinity. I've seen like variants of some problems where like you can stochastically, violate this. Like with probability delta, you violate the constraints. Do you know if that would be qualitatively different than this?
So actually for this generalized Nash equilibrium problem, there is quite a lot of work where you allow for some small violations. So these algorithms take a very different approach. Typically, we are integrating a penalty function or something like that. I guess with the stochastic approach, you can go a similar route, but we explicitly didn't want to do this. Like, we want to integrate these much stronger requirements. Yeah, I don't know if there's something in between that might also be interesting, where you don't take this super radical approach, but maybe are also not satisfied with the guarantees penalty methods can give you. I don't know.
Cool. Okay. Thanks. Anyone else? All right. Well, thanks, Sarah, again.